Planar nuclear medicine gives us flat, two-dimensional views of radioactive tracers inside the body. Single photon emission computed tomography, or SPECT, takes those same tracers and builds a three-dimensional cross-sectional map. This diagram shows the core physical difference between transmission and emission imaging. On the left, a CT scanner transmits X-rays straight through a patient. On the right, SPECT imaging captures single gamma photons emitted from a localized radiopharmaceutical already inside the patient. Because the radiation source is inside the body, the emitted photons scatter outward in all directions, creating an inherently count-poor environment. To collect enough data in this low-photon environment, the system requires time. A typical SPECT image acquisition runs anywhere from 20 to 40 minutes just to register a sufficient number of hits. This sets up this central tension in SPECT physics. Operators must constantly balance the clinical desire for sharp spatial resolution against the physical reality of high image noise. The source radiation is weak and highly scattered. Therefore, every piece of hardware and software in the imaging chain has to be aggressively optimized just to salvage a usable signal. The first point of control in this chain is the collimator, a dense lead grid sitting over the detector that acts as a physical filter to block scattered photons. High-resolution collimators are necessary to ensure the camera accurately maps the spatial origin of the photons throughout the full depth of the patient's body. This diagram illustrates the structural geometry of the collimator. We start with parallel holes, which direct a straight field of view. For the parallel hole configuration to accurately map coordinates, the lead wall separating the holes, the septae, must be perfectly uniform in size. The fan beam configuration, however, utilizes magnification. By angling the holes, it uses more of the detector's field of view to collect data from a compact area, making it highly efficient for imaging the brain. The trade-off is that non-parallel holes strictly restrict the camera's mechanical movement to a purely circular orbit around the target. The geometry of the collimator is the initial gatekeeper. It dictates whether the collected photon data will mathematically reconstruct into a sharp map or a distorted blur. Moving outward from the detector, these multi-head gamma cameras are mounted on a massive gantry, utilizing slip ring technology to rotate smoothly around the patient. Constructing a valid 3D image requires mechanical precision, a constant rotational speed, perfectly parallel detectors, and an accurately aligned center of rotation. Yet the most pressing mechanical variable is distance. As the gap between the patient and the camera increases, the spatial resolution degrades severely. To solve this, modern systems use infrared beams fitted to the collimator face to map the physical contour of the patient's body in real time. This automated body contouring system ensures that the absolute minimum distance between the camera and the patient is maintained throughout the entire 360-degree rotation. To allow for such tight orbits safely, the collimator faces are fitted with pressure-sensitive safety devices that instantly halt movement to prevent any physical contact. In emission physics, proximity is clarity. Every millimeter introduces unrecoverable noise. Once a photon successfully navigates the collimator, the imaging software assigns its strike location to a digital grid, known as the matrix. Modern systems divide the detector into a dense 128 by 128 matrix. In count-poor environments, sparse photons leave many pixels empty, causing severe noise. To compensate, the system downsamples into a 64 by 64 matrix, pooling counts to reduce noise, but sacrificing spatial resolution. Operators can also combat noise by increasing the slice thickness or applying smoother mathematical reconstruction filters to the dataset. Certain specific exams require specialized configurations, the most notable being cardiac SPECT. Because the heart sits off-center in the chest, the camera heads shift into an L configuration. They rotate over a restricted 180-degree arc from the left posterior oblique to the right anterior oblique to minimize physical distance. The system syncs with the patient's heartbeat through ECG gating, acquiring distinct frames per cycle to visualize the motion of the cardiac wall. Ultimately, a high-resolution digital matrix is useless without sufficient incoming photon data. Acquiring actionable, functional images routinely requires sacrificing microscopic detail to achieve statistical certainty. To gather that data, the camera heads collect photons for 20 to 40 seconds per projection frame, moving either in a continuous rotation or a stop-and-start step-and-shoot mode. During reconstruction, the rotating camera compresses detected radioactivity into dozens of 1D profiles, mapping intensity across a 360-degree orbit. A cutoff filter removes high-frequency noise. Finally, through back projection, these filtered lines project backward across a 2D plane, intersecting to build the axial slice. The final cross-sectional image is not a photograph. It is a mathematical aggregate of hundreds of overlapping one-dimensional viewpoints. Even with optimal collimation and filtering, emission physics still faces one major physical distortion: attenuation. Photons emitted from deep inside the body are routinely absorbed or scattered by the dense surrounding tissue. This artificially lowers the measured pixel counts in the central regions of the final image. Software algorithms attempt to correct this by assuming a uniform rate of attenuation across the body, but human tissue isn't uniform, leaving these calculations inherently inaccurate. This animated diagram demonstrates the solution: hybrid SPECT CT. By placing an X-ray source and detector array directly between the gamma camera heads, an anatomical CT scan can be perfectly aligned with the functional SPECT slice. The CT data provides a direct, exact measurement of the anatomical tissue density sitting between the emitting source and the camera. The system uses this structural data to calculate a precise attenuation map. It instantly adjusts and brightens the deep tissue SPECT pixel counts to reflect their true, unobstructed values. SPECT imaging is an exercise in strict constraint management. By marrying the structural precision of transmission data with the functional mapping of emission data, radiologists overcome the limits of single-photon physics to map the body's hidden machinery.